ongoing client education series. My name is Corey Piche. I'm the Director of Sales with Nilex for the Prairies in Ontario, and it gives me a great pleasure to introduce a gentleman by the name of Barry King, who is he is the Eastern Area Manager for Contec. Barry will be walking us through a presentation today focusing on our Ajax products. And Barry, I will send it off to you. And again, at the end of the presentation, what I would ask everybody to do is please hold your questions. Once Barry's completed the presentation, we will unmute phones for any of our guests to either unmute themselves and ask the question, or we also have available our chat line, which you could type in a question and it will be addressed at the end. So thank you, and Barry, off to you.
Thank you, Corey. It's a pleasure to be here. Hello, everybody out there. I'm Barry King. I'm located in Cincinnati, Ohio. I work very closely with the Nilex team on these products, and it is a pleasure to be here today. There is my bio. If you want to take a look at that, it's it speaks for itself. There, I've been with Contec for 15 years, and have specifically focused in armoring against erosion, bridge scour, pier scour, energy dissipation, anything to do with moving water. That's my role here. And so we'll get right into the presentation. Again, if there's any questions, please hold those till the end, or populate the chat, and we can address those at the end of the presentation. So away we go. A little bit of the agenda. The corporate overview, I'll just do that verbally here. Here at Contec, we have a variety of products, with the Ajax units being the Ajax system being the topic here today. But Contec in general, anything from detention, retention, pedestrian steel truss bridges, vehicular steel bridges, plate girder, conduit, precast structures, and of course pipe. That is the main thing that Contec does here in the States. But today we're going to be focusing on Ajax with our partner Nilex, and we'll be talking about some applications, some testing, how you design with these systems. We'll emphasize installation, and then we'll go through some project profiles here in the States, and then I have a few there in the Canadian area. So moving forward here, I just want to take a little bit of a time here to just talk about the legacy of success. And here at Contec, we have been in this business for 100 years, and with respect to the hard armor solutions, and more specifically Ajax. I mean, you can see in the timeline of the development of hard armor throughout the U.S. And about 1991, Ajax came into the fold as a energy dissipator, scour mitigator. And so at that point, you employ that into the systems, you continue your testings, and really find out what this system can do. So looking back through the years, I think everyone can appreciate that builds confidence. These are looked at in a very microscopic scale, so to speak. So we're looking at everything to offer to designers out there. And so anything that you're going to see today is tied to standard, has been full scale tested, and it just has a lot of information behind it, which is readily available if needed. Won't be included here, but just know that anything that you would need to prove to have a proof of concept or a proof of design, just contact your Nilex representative, and we can work together to mitigate your solution there, or mitigate your project and any scour that's needed there. So Ajax, what are they? I know they look like the little units that we used to play with as kids. I'm dating myself a little bit, but they were originally designed as a wave attack mitigation technique, and they were based in that realm early on, talking into the 80s, early 90s, and so what happened there is that Ajax today they've evolved, and so in that evolution, where they stand today is their primary function is to mitigate any inland stream bank bioengineering, scour countermeasures for critical structures. And Ajax are a tremendous dissipator of hydraulic energy. In fact, they were used to mitigate pier scour for structures on the Atlantic coast that are very susceptible to hurricanes, most recently Hurricane Sandy, and we'll get into that a little bit. But they're interlocking high stability units. They come to the project site shipped in pallets, so very, very easy to transport. They can be placed in random or uniform configuration. Both are good and viable for the hydraulics. It's just a visual thing on how you want it to look versus random and uniform. Hand place or bundled placement is also an option we'll get into. And they're an extremely rough layer, and that is one of the main hydraulic benefits of these units. You can see there Manning's N of 0.1, and then that's a general assignment of roughness. As we all know, as hydraulic designers, roughness can vary by depth, and we also have that data at our fingertips here to tailor make it to any project that we might be looking at. So full-scale testing is a standard here at Contech, and the sizes of these units: 2 foot, 4 foot, 6 foot, 8 foot, and 10 foot. And when I talk about size, that is a 2 foot unit. So that dimension is from tip to tip. So when they're laid down, that dimension is reduced a little bit, obviously by the geometry, but when you hear 2 foot unit, just think it is from tip to tip. That is not an installed dimension. And the same goes for the 4, 6, and 8, and 10. Applications. So kind of a myriad there that you can see up in the top left of the slide. You'll see pier scour. You can see the Ajax placed there, surrounding that center pier of a channel. And then to the right of that, a large dissipation pad downstream of an outlet, of a large drainage outlet. And that specific project was for irrigation for farmland. And this one on the right here, top right, that you can see the Ajax down at the toe there, that was for toe stabilization. And really you lock in the toe. That is where the brunt of erosive forces happen. And so you really want to make sure that is in a good, stable condition. That's what you're seeing there, top right. And then bottom left, that's for more shoreline, and what you're looking at there is a weir. And so that's more of a coastal application to mitigate waves. There in the middle is an underwater photo of an Ajax bundle or a module, and that is adjacent to a bridge pier on the Idaho River. So in there to the right, bottom right, you can see those being placed on coastal breakwater there on the lower right. So a little bit of everything is what they're capable of combating, with the hydraulic forces. So today we're going to be concentrating more in the inland scour portion of this. But as I mentioned earlier, any other projects you might have, just contact your NILEX local rep, and we can look at those as well. So testing, we have to make sure they work, right? And that means laboratory testing. And what you're looking at here in this slide is the Manley Hydraulics Laboratory in Australia. And those are just 2 snapshots of those units being tested to combat wave attack, plunging waves on an abutment or an embankment face rather. And across the U.S. we've tested with different entities: Auburn University, California Tech, Colorado State University, my alma mater, is one of the main places where these are tested due to their facility requirements and just how they can test anything. Oregon State University is another entity that's used, and then as well as the University of Florida. So as you can see, all those areas are surrounded by water. In Colorado State, that is specifically interesting because it is inland, but it is supplied by a vast reservoir, and so they can throw just about any amount of water on a system that is needed. So we fail these systems, we understand what they can do, and more importantly, we can understand what they cannot do. So getting into more of the testing and the design. So, technical requirements and testing requirements, when you're looking at these, just some of the things that the Ajax unit has is, we know what it can do with dynamic impact factor and to protect against damage, and drop testing and rollover testing, and what happens to these arms, and really get a sense on how durable they are. Lateral load testing, so that's more of a passive or active pressure acting on these units, and that's another part of the design we can look at. And then factor of safety for shear and velocity. That's really where we concentrate when we talk about pier scour, toe stabilization, anything with moving water. We are going to look for the shear and velocity of that flow regime, and then assign factor of safety based on those conditions. More on the design. A quote from our testing people is, Ajax work very well in trapping sediment, end quote. The average Manning's N for these systems is 0.1, but as you can see by that graph there, and it's just a representation, that can vary by water depth and bed slope. So and also the infill of what's being, for the specific site. So all those come into play, and we can manage those, as we get deeper and deeper into the project specifics. So more about design here. Everyone's seen a free body diagram. I love free body diagrams, but you can really see what's going on here. It is a simple overturning free body, right? Stability is derived, by full-scale testing. And so where is the threshold where that unit fails, right? And so where you have drag, you have lift, and then you have the units acting on each other and independently counteracting those hydraulic forces. So just looking at it on how they fail and how the flow regime is acting on the units, it's not earth shattering. It's things that we've seen before. If you could imagine a rock diagram or a riprap, free body diagram, it would look very similar to this. The difference being is that the hydraulic capacities between the two are vastly different, with Ajax having a much, much higher capacity for those critical structures that you're really worried about. More about the design here. So, one thing, I operate obviously in the United States. And so one thing that I did is I looked at, and I really referenced, it was the National Research Council of Ottawa, and looking at how they view scour and what they use for looking at critical structures or toe conditions, and how they evaluate scour. And I was not pleasantly surprised, but I assumed that they would be looking towards the same criteria that I'm going to be talking about in this slide. And I was correct. Hydraulic engineering circular 18, HEC 20, and HEC 23, that is really the basis when we look at Ajax design for scour. In this case, we're talking about scour for structures, bridges, abutments, piers, things like that. And so looking at the flow of this and how this works. So just like all projects, you have your design guidelines in HEC 23, which you can obviously access online if you really want to dig into the nitty gritty on how these are sized and how to look at these for sizing. Obviously, we would assist with that if needed, but yeah, there's a good design guideline out there in the world that's easily accessible. And so going through the flow of how you would size these for a specific bridge, bridge pier, bridge abutment, anything like that. You know, what you're going to do is you're going to start with HEC 23. You're going to look at your stream stability and the geomorphic assessment. And is it scour susceptible is where you end up in that flow chart. And if the answer is yes, then you move to HEC 23. And okay, let's look at the hydraulic flow. Let's look at the actual water coming through this system and evaluate what that means. And as you work down that flow chart, you get into, you know, down at the bottom there, it says, is a countermeasure viable? If the answer is yes, then you have to go to the next step, which is you have to select your scour countermeasure, excuse me. And so you're developing that. And so it is a very good way to look at your structures that are experiencing scour. It's very straightforward. You go through the design criteria here and really, when you decide that you do need a countermeasure, you're going into HEC 23, and in that document, you're going to be selecting a myriad, you know, from a myriad of devices, techniques, you know, ways to mitigate your scour. And so very easy to follow. And just, you know, just wanted to cover that real quick. You know, what is scour and how do you look at it? Well, it's all right here. And it's not as difficult as you might think. More about design, you know, the ability for Ajax to dissipate energy in a channel, spillway, or culvert applications relies on the inherent roughness of the units. And as mentioned before, the design value for Mannings is traditionally 0.1, which is 2 to 2.5 times the roughness coefficient of riprap. So that really gives you an idea of okay, you have 0.03 for riprap or any kind of rubble material, you know, going all the way up to 0.1, that really gives you a sense on how these units can push that erosive boundary layer out into the flow regime where it belongs, right? You know, where it is away from your pier, where it is away from your abutment or any critical structure that you might be worried about. So when flow encounters the Ajax, the change in roughness creates a very significant reduction in flow velocity. And as we understand, you know, velocity is the main driver of loss of bed material. And so this will effectively decrease the energy associated with the velocity coming into the system near your pier, near your abutment. And you know, it effectively decreases that energy. And as the flow channels through the Ajax, it continues to flow. It's a permeable system. And you know, as I said, that water, once the water hits the Ajax, I mean, you are dead and your velocity is essentially down to nothing. And what that means is that where those Ajax are located on your system, adjacent to your pier, adjacent to your abutment, the velocity does not have the ability to dislodge those bed material fines and hence cause erosion, right? And so that's really what we're looking for, is to mitigate those forces that are going to carry our stream bed away. The question that most designers ask me is what do I need to specify these, right? You know, what is needed from the system point of view? What do I need to look at? And the answer is, you know, it's the same information that you currently use to design with riprap, let's say, or any kind of you know, scour countermeasure or revetment device that you use, you know, whatever your favorite might be. There's nothing special here. You know, you have site geometry, you have flow data, and then you have a methodology available to you that just essentially tells you exactly what to look for, you know, and how to size that. Very, very good design guidelines. And so it's very straightforward. The important part of this is to have your site and geometry right and have a good understanding of your flow data. That is the critical part. The design methodology takes care of itself, and it is very well founded and proven throughout the years. Installation. This is, my favorite subject. One of my common phrases is, when I look at a set of plans, that is construction in heaven, right? Nothing is ever depicted in plans of what you see on the site. So to be able to be versatile, to be able to address challenges on site in an expedient manner, that lends itself to these units. Okay. And we'll get into that a little bit. The installation of these units, they're typically, it depends on the unit size, 2 foot, 4 foot, 6 foot, 8 foot. But traditionally we're using 24-inch units, sometimes 48-inch units. Really because they are so robust, there's not a whole lot of flow that can dislodge a 48-inch unit is what we found out. And so traditionally the smaller 24 units are individually hand placed. And so you can actually pick these up and set them into place. Now, I'll get into that a little bit on this slide. In that photo you're seeing, that's a bridge bent in a very fast moving river in Ohio. And that's a temporary vent you're seeing there, and that, they put that up to really support their bridges or support that bridge deck, because if you're looking at the picture, you see to the right of that pier bent, that has all been scoured out, and so much so that it's got underneath the supports up above in the top foundation there at the top of the slope. So this is eroded so much that you are now losing structural stability of that critical part of your bridge. In this case, they installed 1,000 units a day, which is very easy to do. 4-person crew. You have an operator there. If you look real close, you'll see a gentleman on a skid steer down in the flow, and he's bringing the units to the 2 gentlemen that are hand placing them around that pier bend. The key here is to have the units delivered as close to the final, and this is when you're hand placing. You want to have the units that arrive on pallets, you want those as close to the final landing spot or where they're going to be installed as possible. That's not always the case, and we can talk about what that means. But when you're looking at hand placing, you want to get those units close to the final placement area, and then it's a matter of putting them together and getting them in the defined area of scour, which is what you're seeing here. Other techniques, the contractors teach us all kinds of very good tricks and ways to be expedient in the field, and for larger applications, groupings or modules are really effective. And this is larger scale where you can get a lot of units down at once, and really specifically submerged conditions. They really prove their mettle there. If you can imagine, you're dropping in the column of water, on the coast of New Jersey. It's been upwards of 30 to 40 foot of water, and very easily done. And we talk contractors through that when it comes to it. It's about a half-hour conversation, and then the contractor says to me, okay, you need to get out of my face. I have to go make some money. So it is that simple. But there is some guidance that needs to be supplied. So as you can see here, the left photo, that is a frame that a contractor welded together to place these bundles. And then in the right, there is another fixture that was created by a contractor, and this is more of an embankment armoring, but very good picture to look at there, because you can see what they're doing. They're tearing this up, very erosive environment there, and so they really needed to keep that embankment stable. As we all know, open land is not being created anymore. And so whatever you have, you want to keep it. And so steep embankments and armoring those up to keep that footprint where you want it is something that Ajax can help you with. And they bundles can vary in size. What you're looking at here in this photo, this is a photo on the North Carolina coast. And there is a very resort driven area of the Outer Banks there. This is the Oregon Inlet, and they had a very bad problem with bridge scour off the coast there. They were losing their pier bents, and so much so that they had to close the road many times. Since the Ajax have been installed, that is no longer the case. They're mitigating those critical piers as needed and as designed. And in this case in particular, you see that mass of units there. Those are 48-inch units. Each one of those units weighs about 600 pounds on average, let's say. So you can really get a sense of what the contractor is lifting there. And the reason why they did it this way is it was the tidal velocities that happen in this specific area. Hence why the bridge has so many problems, right? You know, you get very high tidal velocities right through this channel in the Oregon Inlet off the coast. And so they had about an hour or two to really be efficient in their work. And then the tidal velocities at that depth got so swift, they could not, you know, it was unsafe to place anymore. So placing that large bundle to maximize that 1 to 2 hour placement time was critical. And you can see again what the contractors can do. This was all them. You know, they know how to rig. They know how to lift, and they know how to be efficient. And I wish I could take credit for what you're seeing there, but this is all the contractor. The ocean depths in this case, they varied from 30 to 60 feet, depending on where that pier was located. More about installation. Obviously a great solution for bridge scour, as we've said. HEC 18 and HEC 23 references, gone over that. And frequently bundle placement with divers for direction sometimes. And I know the diver piece is, what do you mean divers? Well, usually what we see with that is for inspection. Are they where they should be? And since then, we've seen GPS location, we've seen all kinds of efforts by the contractors to pull that diver out of the equation, so to speak. Now, is a diver always eliminated? Absolutely not. It depends on the project, okay? And it depends on the criteria around that, the inspection and those kind of things. So just another, and this is obviously in 2002, so that gives you a sense on how long these have been around and how long they have been serving the bridge community out there. So I'll get into a little bit more specifics in the project profiles in the upcoming slides. So pier and abutment scour. This is really where they will shine. And, you know, you're underneath bridge decks, things of that nature, sometimes in deep water, moving fast. What does that mean, right? And so let's go through a few examples and try to address that. And so this is a project I was involved in. It has a funny name, Route 35 over Cheesequake Creek. I can never get that right. It's in New Jersey near Sayersville. And what you're looking at here is a plan view of a vertical drawbridge. They had some major scour around the main pier beds here. And I'll advance some slides here. Maybe you can see, well, let me go back. So yeah, this is what you start with. And so they've located, they've identified where their piers and where their abutments are being undermined, quite frankly, and affecting the structural integrity of this critical, you know, vertical drawbridge. And so looking at our, you know, context, this is what we put forth as our design, and you can kind of get an easier plan view there. What you're looking at in the center is the main navigation channel. And then you have your fender structures on the right and left of that to keep the vessels from impacting any of the abutments or pier bents there. So that's kind of what you're looking at in context view. I'll get a little bit more granular for you. Here is, you know, one of the bridge piers, and so you can see what's going on here. In this case, they use, you know, in this they're calling them 6x6x6 matrices. Well, that is an Ajax bundle, and so you can see how they are placing that around that pier to combat their scour. And so that was a detail from the plans. And this is the navigational channel where not a topic for this presentation, but for that navigable channel, they used ACBs. ArmorFlex is what they used there, which we've previously give webinars on. And then what happened is Hurricane Sandy came through. So this is the drawbridge. This is days after Hurricane Sandy and I got this from the New Jersey Transit Authority. So you can see what happened there. We have boats, we have large containers. You can see what is going on, just destruction, right? And Sandy, if you know, and I know this is a Canadian group, but Sayersville, New Jersey is on the coast. That was essentially the entry point for Hurricane Sandy that impacted the states. Right at the leading edge. It was right here at this structure. So of course I called up and talked to the owner, talked to our local representative up there, and where the scour countermeasures and where the Ajax were placed here, and you can see them there kind of crosshatched there on the left. That's where they were placed, and this is what they discovered at low tide. The units were exactly where they had placed them, on the bed adjacent to the bridge pier. And they surveyed this later on, and they did not find any degradation, i.e. there was no bed drop. The elevation where these units were set, where these bundles were set, were still intact after that category 4 hurricane that impacted right there. So I'm like a proud papa here, because that is there's no truer test. And it was really nice to see that. You do your math, you do your construction, but then this happens, and so you really, okay, what did we get right? And I wish I could take credit for the robustness of the system, but the Ajax did all the work here. We just worked with the contractor to get them where they wanted them. Another very nice project. This is in Idaho. One of our signature projects for Ajax. It was on the top 5 kind of ranking for the Idaho Department of Transportation due to the critical connection between Western Idaho and the north and south part of the state. So there's kind of a juncture there where this structure, the Clearwater Bridge, that's the only way to go. So it has to be there. They have to, it is crucial to the regional area. And what they had found is they had major scour along these piers, and it's a very good shot of what we're looking at. These rivers out west during the melt, they can really get raging and really cause havoc. So in this case, piers 1 through 8 were protected. There were a total of 15,000 24-inch Ajax on this project. Pier number 1, which is all the way to the left there, that you can see in the slide, it's the one all the way. That one was more, and there was it was a dry condition. When these were placed, they were in the dry, and knowing that was going to get inundated in the runoff, but the contractor used that as a place to practice. How do you swing these? How do they behave? How do I get efficient? And so that's really what they used that first pier for. And once they got their practice down, which lasted, I think they got that down within a half day, then they proceeded to make hay. They proceeded to get efficient and really get these units in expediently. That's what contractors like to do. They, time's money. And so anything they could do to be as quick as possible can only benefit them. And it was very easy to do here. More on this project, you can see this is kind of where they were looking, to place adjacent to a pier. You can see the flow of the water. You see that eddy there, and you see kind of how that flow is working. In the water installation, it was in 1 to 4.5 meters. The water velocities for 2.5 meters per second to 4.5 meters per second. And the contractor built this spreader bar to get the modules down. Now you can see there was a, hey, okay, let's see how this behaves. And you can see how the current's acting on the bar, and, they're ensuring that that is in the position dictated by the designer. About 10 minutes of trial and error. They can gauge how the flow is that day with the velocity, and then they do the setback, and they can get those in. Even with that rapidly flowing water. So just a testament of how that contractor really made this job. And as a result, what you're looking at here is, so they did a big study on this, and it's the Spalding Bridge. The transportation, they were awarded an AASHTO award for this, and they were awarded the AASHTO President Awards for best practices. It was really good to see a very complex structure, but a pretty straightforward install, and that's really what made it here. And more importantly, it worked. And not only did it work to where it was getting awards. So more of that to come. You can find this project online and look at it more in depth if needed. But yeah, just to kind of sense the scale of how we work. That was a good project. So very good success. But then you can go to smaller projects, right? So in this case, this is in Ozark, Missouri, and originally protected by riprap. The Spring Creek Bridge abutment was unable to withstand the continual flows that the stream, it's very flashy through there. So you get very high velocities. And so really what was needed here is that they needed to keep the back. And what was happening is that the abutment on the right-hand side of the left picture, that was all undermined. It was getting into that top, footing structure, and they were going to lose it. It was critical. This one got fast-tracked. And so what do? I talked about toe stabilization. And so really to work with the designer, to work with the budget, and hey, we've got, we know the Ajax will work, but my budget, I really, how can I incorporate rock in here? And that's done every day. I'm a big believer in combination systems. So in this case, you're looking at toe stabilization. And so you can see 2 rows of the Ajax there, and just really locking in that toe and not allowing those erosive forces to undermine that slope. Because we all know what happens. You have a slope, you get the toe undermined, that slope steepens up, and then it fails. And then the process happens again. So this halted that process. So yeah, just another example of how these can be used for bridge scour, both large and small, this being on the smaller variety. But I wanted to get more specific to Canada, right? And I received a call a few months back, and working with the NILEX representative, I got a call from McElhaney Engineering. They have a structure that's very remote. Structures, and that's sometimes the case. So this is located on, south of Prince George on Red Rock Road West. I don't know if anyone's been there, but looking it up, it is fairly remote. Okay, so you're in the northern reaches there. You can see where that is, obviously. And there was a reason why the designer wanted to use and was really looking hard and ultimately designed with the Ajax, it was really about how to get the scour countermeasure there. Do I use rock trucks? Well, that's, and how do I install underneath this structure? And so let's look at the structure. And so just the robustness of the small unit versus the large stones that they were proposing, it just made sense. And so getting into the design a little bit, you can see what's going on here. The abutment, you have a combination of timbers, and there's some concrete in there, and you got some riprap at the toe. And what they were looking to do here were they wanted to install some new timbers. They wanted to remove all the vegetation and all the failed riprap that was around the toe. And so this is what's left. Initially, this was all the way up back onto the abutment, about midway through those timbers in the top photo in the east ballast wall. And you can see a good repair, typical section there of what they were going to do with the piles and the new, the whalers is what I call them, the actual supports in between those piles. This is the final design. And like I said earlier, combination, design and using different materials, that's pretty normal and very consistent with how we work today. I mean, if you don't have something that requires this robust Ajax, then like you see here, when you get upstream and downstream into this bend, and that's really the problem here, is the location and the severe 90-degree bend, which is taking out all the very, apparently sized appropriately riprap, but it's being lost, right? So this is the final design that was done. You see the riprap upstream, you see the riprap downstream, but there in the barrel or in the structure itself, you can really see what's going on. And I'll kind of show you what's going on. And this is the structure of what you're seeing. And so you can see, this is underneath in the previous photos. This is what they were going with. And when I say going with, they designed 24-inch Ajax units tiered at 2-to-1. So you can kind of see, how they address not only the hydraulic flows, but the geometry, right? He wanted to have that protection up on about midway through that pier bend. And so that you're seeing a stack here. So you have 2 on the bottom, 1 on the top, and that's to get that overall vertical height that you're trying to achieve. And then in the final condition, you use the smaller rock to choke that. Well, in this case, McElhaney, they really wanted to choke those units. They thought that would provide some benefit. Me personally, I was not concerned. It's fine that they do that. But when the gully washer comes through, when the spring thaw happens, I think some of that smaller material is going to be evacuated and you're going to be left with the Ajax scour countermeasures. And what's going to happen in the receding limb of that hydrograph, as that velocity slows, as that runoff kind of, as you move further and further into spring, you're going to get deposition of bed material. You're going to get, that's a function of the velocity just being knocked down. And so you get this, sediment laden flow coming through this system. It runs into this rough countermeasure and it deadens your velocity, and you do get dropout of sediment. And what we see and what the scour or what the bridge inspectors tell us, and all around the country down here, is, hey, I went out there, I thought they were gone, but I poked on it a little bit and they were 3 inches beneath the deposited sediment. Now, if they would have went back there during the fall, that sediment wouldn't have been there. But back to the deposition in those lower flow conditions, that is the expectations. These will fill in and even provide more stability. Not that it's needed, but that's the way they work. So a lot of deposition can happen. Talk a little bit about energy dissipation. And yeah, sorry for looks like I doubled up on some titles there, but that's okay. This is a New Jersey project in Route 287, and they had, New Jersey is a wild area. When you think of New Jersey, you think maybe of the Sopranos, right? There is a lot of hill country. There is a lot of farmland. There is a lot of horse country, a lot of stuff going on in New Jersey, a whole new appreciation as I've been servicing that state. But in this case, they had I think it was a 36-inch culvert pipe coming underneath a road and then discharging onto an embankment. And I'll show you some more on that. So that's what they were looking at. So you can see in this photo, or in this plan set, you can see where the existing ground is, which is that kind of undulating, that lower line right here. right through here. That's what they had. And that was a result of this pipe discharging, impacting on this slope and just eating this away. And it was going to continue. And so the worry is that you have Route 287 just uphill of that, and very busy road, even for this rural part of the state, that they were going to lose it. They were already seeing the flexural cracks in the asphalt. They were seeing their guardrail posts kind of changing direction. They knew that the slope was moving. And then came the Ajax. So in the final condition there, you can see what they did initially. They tried to use the rock. So that rock was in place downstream of the units. On the first discharge, the first event that happened out of this pipe, that rock ended up downstream. And so they knew that they needed something else. Looking up at the pipe and really getting a sense of what is done here, right? And so you can see the pipe discharging onto the units. One thing that I want to point out in that center picture, you can see the Ajax, in the forefront, but down the slope, you can see where the stream's trying to find its outlet, right? Well, there was a second to this because the Ajax were actually continued all the way down where they wanted the flow to go. They wanted the flow to be directed to a certain area. They didn't want it to find its own channel once it got off the initial phase. And so what we saw there, what we saw was a continuation of this based on the success of the uphill units. A very good success, saved hundreds of thousands of dollars in the mitigation. If that road would have started going, it would have gotten really expensive. So this was a drop in the bucket compared to what they were faced with if things continued as they were. So a little bit on dissipation there. Another one, this is in Montana. They call it Dead Man Basin. I kind of alluded to this a little bit on the first slides, but this highlights the ability of Ajax to dissipate the energy associated with the hydraulic jump. In this case, the inbound design water velocity was 8.5 meters per second, and the hydraulic jump surged as high as 4.5 meters high, depending on the outlet conditions, right? So the units that were placed, you can see the top left, you can see those units being placed in the dissipation pad. You can see it being activated in the center, and then the top right, you can see kind of the result of what happens there. When I talk about deposition, that's what you can expect, okay? That's the lower rescinding limb of the hydrograph, and you got deposition throughout all those units. Now, when the design event comes through, is that going to get blown out again? Absolutely. But again, in that in that healing receding limb, this top right picture is what you can expect. This is a project in Georgia, and it's a spillway that's going to be outletting into you can see where it's going to be outletting essentially into a creek adjacent to a forest. And so they had the spillway they had the spillway designed. And by the way, that's Ajax, or that's Armorflex there in the forefront of that left-hand picture. But then they needed to get a dissipator. They said, okay, we've got water screaming down here at 20 feet per second. Excuse the English units there, but I think it was 20 to 25 feet per second. I think it was more on the 25 feet per second. So they needed to knock the energy out of that, get it into a velocity where it would not erode on the downstream side. So in this case, you had, and you can see the field of Ajax on the right-hand side. They had velocity coming in at 25 feet per second, and then it was 35-foot pad they had on the downstream end of that Ajax dissipation pad. The velocity was reduced to 3 feet per second. So not any kind of velocity that would erode these soils around here in this lakefront sports community spillway. So just another example of how they can benefit, right? And this is a more involved project here. This is also in Georgia. So just in short, what you're looking at there in the right-hand picture, you can see the interstate there. They were very concerned. It was all about the interstate. They had they had to route water through, into Noonday Creek underneath the bridge here. They had tried, just about everything. And I'm talking about 10, 15 years of trying to combat this, because the discharge facility, that wasn't going away. The discharge was still going to happen through this system, but it was getting into an interstate and it was getting into their piers, and it was a maintenance nightmare. So in the final design, the state of Georgia said, you know what, we're going to get this. The maintenance is done on this. We need something that works. We need something robust. What do we have out there? And working with Florence and Hutcherson, the designer at the time, they contacted us about our Ajax units. And so the design challenges, we had overtopping flow at the design event, significant scour at the base of the outlet structure. And we needed to protect the bridge piers. And so the solution, 48-inch Ajax on the side slopes, or for bank stabilization, and a little bit, for the pier protection. Well, I'm sorry, excuse me, 48-inch units were installed for the pier protection. Again, they wanted to be heavy-handed here. It was 15 years of combating this and just throwing money after money. And then the 24-inch units, they were installed in the basin to make sure that basin, when the overtopping happened, was also sound. So again, picture in the left-hand side, 24-inch units in the basin. And then you can see, as you look up next to the bridge structure, you can see where the 48-inch units are around that embankment, going through the structure and providing that protection that they needed. Just wanted to mention, this also received an award by the state of Georgia, the DOT there. It was a very good success. And believe me, I would know if there was problems here. And this has been in the ground for 10 years, have not heard a peep, have only seen pictures of it functioning as designed for the last 10 years. So very, very nice project there. So just a little bit more of what they can do, right? Streambank Bioengineering. This is Oak Meadows Golf Course in Illinois. They were, just like most man-made lakes, they were losing, some of their embankment, the bank of their lake. And I know it's not moving water, but what was failing this was wind-fetched waves. So it was a fairly large lake. The winds would push out and just create these waves that would impact, in this case, in the center picture there, you can really see it's right adjacent to homes there along the golf course. And so in this case, stabilize the toe, lock that in, and then use softer, more economical solutions upslope of that. So on the bottom right-hand picture, you can see that being done. If you look real close, you can see the Ajax units, right there, exactly where they were placed, combating that toe scour, combating that toe, making sure that toe was stable. And then everything upslope of that was, turf reinforcements, mats, riprap, things that are more budget friendly. So yeah, just another combination there for you to, and then, just another application. Here in Carthage, Indiana, kind of the same thing. In this case, this was a riverine environment. So you can see the gentleman placing the units there on the left, but on the right, you can see the gentleman standing there, and behind them, that's the White River. And in Indiana, that river causes havoc. And they needed to make sure this river stayed within his banks. And was it because, the farmer that owned the adjacent property was worried? No. What drove this project is, up above, they had just done I think it was a $50 million road improvement. And in doing so, some of the drainage had changed. And as the flow happened, they were starting to see embankment scour getting towards that freshly constructed road project. And so they wanted to say, we can't let this river move over here. What do we need to do? And so it was establishing the toe, making sure that was a bomber point on the design, and then this is what you have in the interim. So you can see, or in the final condition. So you can see on the left of that picture where they're using some turf reinforcement mats, some other more vegetative friendly things, but about 2 feet out on that toe or out from that edge of water, that is where the Ajaxer unit are located, doing their job to this day. So this was done in 2014. I talk with the DOT quite often. I always ask about this project. There's been absolutely no problems. Believe me, I would know. The taxpayers of Indiana would let their people know, and then I would know. So yeah, effective and a very good project, and exactly what they needed here. In Texas, another toe stabilization. This is in concert with a bridge structure. So you can see, again, toe stabilization, and then you can go with turf. In this case, sod. They went with some turf reinforcement on the other side, but lock in the toe and then pretty up the back slope, you know, in layman's term. That's what we're looking at. This is right after construction. So, you know, probably get an updated photo here. You would see what you saw in the previous. These essentially disappear. Once you get vegetation really growing, you know where the toe is, and it essentially disappears. And then a little something else. This is stream barbs, and so you can see what's going on there. And so you have a series of barbs that were constructed out of the Ajax units. And if anyone knows anything about that, you know, stream barbs, it's really a dike. It's really kind of a weir configuration. And what you're trying to do is force those erosive forces away from the place where you don't want them to act. That's why they were installed here. So just a myriad of ways to use these. Bridge scour, pier scour, abutment scour, primary uses. Very good for that, as McElhaney Group realized and is designing today with. But they can be used for bioengineering, redirecting rivers to where you want them. You know, hey, stay away from here. We're armored over here. Go over there and get the sediment that you crave. And I'm talking to the flow regime here in a metaphysical sense. But yeah, I mean, you have the flow, and that water wants sediment. I mean, that's a natural process. Sediment transport, right? Lanes balance. That's what we understand. But you don't want it to take that where you need that soil. And so that's where these can really help you. And in this case, in Fountain, Colorado, that's exactly what they did. That's the end of my presentation, and yeah, it went by pretty quick. So I hope you enjoyed it. I hope it was effective. I hope you can address some of your problems with the Ajax units. And if you have any questions, please let's hear them. Thank you.
It would seem to me that we would need to have you or somebody present this to the designers of our provincial projects. Is that something you do?
Absolutely. And when the border opens up, I can come up there personally.
Perfect.
That is not a problem. That is one of my main functions. And you know, I'm an engineer. I'm a professional engineer. But one of my common activities here at Contech is to promote and talk to groups exactly how you mentioned there, Jamie.
I have to say,
yeah, I would just a little bit more there. Just talk to your NILEX representative, and we can set that up. That is the main point of contact here. So always talk to NILEX first. They are your regional first touch. But always know that Contech here and me personally and our team, this is what they have behind us. So behind them. So if things like that are needed, absolutely. You know, to talk to the provincial, you know, the boards and really show them what these can do. Yeah, that's something that we would be very interested in doing.
Lucy here. I have to say that I know you guys have the plastic models of the Ajax, and I found those super helpful for dealing with contractors and even other designers in the office to like, because people see them and they're like, I don't understand. Like the physical, spatial, like even contractors too, they're like, they see the drawings and they're like, cool, but like what are these things? So having like being able to get your hands on the actual physical, like small, they're like little toy model things, I found has really helped, because you can like have your pre-meeting on site and like discuss how everything's going to go together with these little blocks, and then you can start moving people to the actual big, like the 24-inch ones, where, because you know all our projects hand place them, so you're like, okay, let's start setting it up, and like once they get it, it goes together so quickly, but you have to get over that hump of like what are these, how are we doing this, like we need help.
Well, you touched on it right there, and that's, you know, I was in Pennsylvania 3 weeks ago or a month ago, and there was, you know, 1-to-1 slopes, brand new bridge being placed, and they had major scour in Pennsylvania. And so my job there was to get with the contractor before they were going to placement and make sure, A, that they knew what they were doing, B, that they were building bundles and orienting these units correctly. Now I flew up there, drove to the job site. We had scheduled a 4-hour meeting to do this. And within 45 minutes, which is typical, they were bored of me talking about the installation. They got it, they understood it, they wanted to go make money. And so that's the typical, but you are exactly correct. I mean, looking at these and trying to, you know, hey, how, and with contractors specifically, I mean, the product of them not understanding something that is on plans is their price goes up. So that is a critical point. You know, these are very versatile. The science is the science. They are very robust, very well tested. We know they work. But if a contractor doesn't understand how they're placed efficiently and how easy it is and how versatile they are, that's the point that you really have to hit. You know, I wish I could say I developed these and yeah, I knew that the hydraulics were going to be combated very well with these, but that's not the case. Where I like to shine and what I really emphasize is exactly what you're talking about, making sure the contractors understand it, and it usually goes pretty quickly.
Hi, this is Khalid here. Just have a question. I know this technology does look quite promising, and we have done it on one of the Ministry of Transportation's project, and we're also looking, Holsworth is also a project. And though I'm still curious in terms of their performance, if we happen to have scour more than anticipated, so what is the performance, the behavior of the Ajax at the toe in terms of flexibility? So how far?
The flexibility?
Yes, how far they are flexible to conform to this cover if it happens more than.
No, I'm with you. I'm with you, and that's a very good question, and that sometimes eludes me. But yeah, as far as the bed form, and we're talking about, you know, toe stabilization in this case, but we can take it into bridge scour if we want and submerge. But as you know, the bed form, it is going to be what it's going to be. And you know, here in the States, depending on the permitting, it might be okay to you know, get that bed form what you want it to be, but that's a rarity. Okay. You know, typically you have what you have, and you have to be able to conform to that bed form, right? These do that very well. And why I say that is there's a few rules on the spacing. And when I say spacing, center to center spacing of units. So they can be very tight, you know, just against each other, just very tight, and there's no space. Or they've been tested to be farther apart with the same capacity. I mean, there's no change in their in their hydraulic capacity, i.e. how to combat velocity and shear forces. And so to your point, as that spacing can vary, I mean, you can really get into, conforming in a bunch of different cases. And as I mentioned, and, kind of in the forefront, they can be placed in a irregular fashion, non-uniform. So there's a way to get them together, and yeah, they look real nice and they fit together, but they can be placed in a random configuration. And when you're talking about changing bed forms, that is where that can come into play, both the spacing part of it and the randomness, depending on what you have there. Hopefully that answered that question. I mean, my experience with large scour projects, I know we were talking about, bed form and hugging a toe, and that is probably go back a few pictures and show you where we did that. But there was a project on the Hudson River near New York, and they were in 50 foot of water, and they were placing these in bundles. And the report came back from the contractor that, hey, they did a bathyspheric survey of the underlying, that was 2 years ago. Well, this is what it looks like today. And he described it as the Grand Canyon underwater. So very, non-uniform undulations of bed form all around these piers. I mean, if we've ever seen a pier scour hole in the dry, I mean, it's not really uniform. I mean, there's a bunch of stuff happening, and it's high over here and low over here. It was not an issue for the Ajax, and I know that because I check up on these. Those large structures. In that case, over the Hudson River, they placed 88,000 of these to save that structure. And if they didn't work and that structure was jeopardized, we would be the first to know. So those have been installed for about 8 years now. No, longer than that, 12 years. Bridge scour inspection on that structure is done every 6 months due to the critical nature of that Hudson River bridge that I'm talking about. And so that data is there for us. We know that they are exactly where they were placed, doing their job. And, depending on where they are in the flow, either upstream or downstream, some of them were completely buried, 5 or 6 inches of bed material. Others, they're more on the forefront, the tops were exposed, but that was it. So, but in all cases in that application, the bed form was very undulating, i.e. the Grand Canyon underwater, according to the contractor, and the units conformed just fine.
Well, thanks. Another follow-up question, if I may. Comparing this with ACM, articulated concrete map, do you think that, by what you just showed, looks like that this probably is a good technology for at the toe or in the channel bed? Probably not so for the channel slope. So when it comes to the channel slope, probably ACM would perform better. Is my understanding correct?
Yeah, I mean, in a general sense, yes. But, from where we stand, we're always looking at the hydraulics, right? So, if your stream bank is, the banks of the river or the stream, the flow regime, whatever you have there, if the flows are enough where it is outside of ACBMs, you know that these can be used. But yeah, I hear what you're saying there, and I would concur with you for sure. There's a few things about that on the installation when you compare ACBMs versus Ajax, and it talks about, per the standard, it talks about preparing the bed and what criteria is needed, and how you do that subgrade. That is a big difference between the two systems, where the ACBMs can be a little bit more restrictive on how you build up that, and i.e. how you would have if you were on an embankment, that wouldn't be a problem because it's easily accessible. But when you're inundated and you have water, the question of how do you get that subgrade right, that really does not coincide well with with ACBMs in a general sense. I mean, it's obviously been done. I had a project on here, Cheesequake, that was done in a submerged condition, but yeah, I mean, it's much easier, and the subgrade preparation is much more forgiving for the Ajax, and that's what I would recommend for anything like that in the bed. So yeah, you're right on point there.
A very good question.